Hello everyone, it's Jason from Skinny Research and Development. Today what we're going to look at is the math behind the 555 timer. Now I did make a video like this in the past, but I just wasn't satisfied with it. You guys had some great comments and some things that you would like to see in the video, and so I wanted to make the video better. So in this video what we're going to do is explore the formulas of the 555 timer, how those formulas came about, and then look at a real-world example on how I would pick components to go with the 555 timer in order to meet a certain frequency range that I'm trying to hit. For instance, I needed this circuit board a few days ago to hit 40 kilohertz exactly, and I'll show you how I got that. So here's the deal. If you are interested in figuring out how the formulas for the 555 timer came about and where they come from, you can just continue to watch from this point on. If you're more interested in how to deal with the formulas and how you take the two formulas from the data sheet to get the formula that shows you how to arrive at the frequency, let's say you can look right here. But if you're in it just for the example, let's say you have a 555 timer that you are trying to get to output a certain frequency range. You have an idea of the components you want to use, but you don't know how to manipulate the formula to give you what you want. I'll show you my example and what I had to do a couple of weeks ago to make this circuit board, and I will put it, say, right here. So those are your options, so stick with me if you want to listen to the formulas, or if you would like to choose one of the options, go ahead and do so now. The brown paper bag has already been attached to the desk, so let's get started. So before we get started, it'd probably be a good to review what we've already done in previous videos, and that's just how to set up the 555 timer as a clocking mechanism. This has been cut straight from the pages of the data sheet, and we have our different 8 pins here of the 555 timer. Pins 8 and pins 4 both get connected to 9 volts. Pin 1 gets connected to ground. Pin 5 gets a capacitor on the control voltage pin. This capacitor is usually 0.01 microfarad, and it goes to ground. Pin 6 and pin 2 are connected together. Then this is kind of where everything happens for the 555 timer to make this into that steady clock. RA will be connected between pins 8 and pin 7. Between pins 6 and 7 will be RB. And then between pin 6 and ground will be the capacitor C. And what we've said in past videos is these different combinations actually determine the timing for the clock that you're trying to create. The way it works, this 9-volt battery in this case is charging up this capacitor C, and RA and RB is kind of hampering that capacitor from being charged. And so what's going to happen is this capacitor first will charge up through RA and RB. Once this capacitor is charged to 2/3 of the source voltage, then that will trigger this comparator and will also trigger this flip-flop, which then affects the output stage. But then at the same time that this reaches 2/3 of the voltage source, then the capacitor is going to be discharged into ground through RB. Current flows through RA and RB to charge the capacitor, and then when the capacitor discharges, then current is going to flow through RB to ground. Based on the timing of this capacitor charging and discharging, you will get a certain frequency rate on the output. By setting RA and RB and the value of C, we can set the frequency that we want this output to be. Now, choosing values for RA and RB and C, that's where the math comes in. What we're going to do is take a look at where you would look for any math involving a chip that you would buy off the market. Go to the data sheet. So this is the data sheet from the 555 timer that I'm using. This is page 11 of the Texas Instruments data sheet, and it tells us that in order to figure out the frequency, that we have this formula down here that we've looked at before, 1.44 divided by RA plus 2RB times C, and that will give us the frequency at the output. But it also goes a step further and says, hey, if you just want to figure out the charge time or the output high time of the 555 timer, use this formula. It's 0.693 RA plus RB times C. And if you want to figure out the discharge time or the output low of the 555 timer, then this formula here that says T2 equals 0.693 times RB times C, that will work. So we're going to look at why these formulas exist and why they exist in the form that they do. So what we see from the data sheet is that the amount of time that the output is high is given by this formula, T1. And the discharge time, or the amount of time the output is low, is given by T2, which equals this. So the amount of time it takes to charge this capacitor has something to do with adding the values of RA and RB. So that's kind of a delaying factor for the current to go through RA and RB to charge capacitor C. So yeah, you can kind of see the amount of time it's going to take to charge this capacitor is going to be dependent on the current flowing through RA, RB, and then charging C to whatever value, in this case 2/3 of the source voltage. And then also for T2, you can see that, well, the only thing that's involved in discharging this capacitor is this transistor is going to ground, this capacitor is going to discharge only through RB. So you can go, okay, so that formula kind of makes sense. But the question is, where do these values come from here? This 0.693, is that just arbitrary? Like, what's going on? Why are we using 0.693? Some percentage value maybe, or some sort of fractional value of this charge? So let's take a look at why these formulas make sense. So to make sense of this, we need to look at something called the RC time constant. Now you see this written all kind of different ways. You'll see it written as a Greek letter, sometimes just T. I'm just going to tell you that the way this works is that if you take some value R, you multiply that by some capacitance C, that's going to give you some value of time. So it makes sense that when we're looking for time 1 and time 2 over here, that whatever we multiply out here should give us some value in seconds, some value in time. So if you multiply R times C, you're going to get a value in time. What's interesting about this is that when you have a circuit that looks like this, the value that you get from multiplying R times C is 1/5 of the time it takes to charge the capacitor. In other words, if you go 5 times RC, this is going to give you the time needed to charge C. So one thing to remember is that a capacitor is never completely charged, but what we say is that it reaches a steady state. In other words, it is charged as much as it's going to charge. So if you wait 5 times whatever R times C is, you will have completely charged the capacitor. So something else to notice about all of this is that as the capacitor is charging, it doesn't charge in a linear fashion. So let's take a look at this on a chart. So first off, let's label this time axis here. And instead of labeling this as an actual time, I'm going to label this in terms of R times C. So what we said is that the capacitor will be fully charged at 5 RC, and it will be fully charged to the amount of the source voltage. And we also said that it's not linear, so that means it's not just going to be a straight line up to 5 RC. It actually looks more like this. So as the capacitor starts to charge, you'll see, unlike some linear line that just goes straight up at a 45-degree angle, you'll notice that initially the capacitor charges very quickly. And so it slowly kind of tapers off the speed, I guess you could say, at which it's charging the capacitor. So this line is described by an equation, and the equation is fairly nasty, but it's not too bad. It's that the voltage across the capacitor equals voltage source times 1 minus e to the negative t divided by RC. So let's just say we wanted to know the voltage across the capacitor at time RC. Let's say time RC is 0.01 seconds. So up here we could say, okay, the time that we are looking for is 0.01 seconds. We divide that by RC, which we already know is 0.01 seconds. All right, that will cancel out. Now we could do this formula just generically too. We could just say, all right, at time RC, so it would be RC over RC, cancel out, so it would be e to the negative 1 at that case. So we can take our calculator, we can go source voltage times 1 minus e to the negative 1, and what we end up with, if we just take this part of the formula, is we would see that the capacitor voltage equals the voltage source times 0.632. Okay, so at time RC, the capacitor voltage is some fraction of the voltage source, and we know exactly how much that is. It is the voltage source. In this case, let's say 9 volts. We go 9 volts times 0.632, and we would find out that at RC, the amount of voltage across the capacitor is somewhere around 5.69 volts. Okay, so this is all good and all, but I'm going to put this over to the side because we still have a problem. So let's take a look at our original formulas. T1 equals 0.693 times RA plus RB times C. So this is a resistance, this is a capacitance. Oh, look, we're going to get a time out of this, we know that. And what this is saying is the amount of time that the 555 timer is going to be high is equal to RA plus RB times C times this value, 0.693. Well, what is 0.693? If we did 0.693 RC, okay, what are we going to come up with? What's the value we get out of this equation if we say, okay, I want my time to be 0.693 RC? What value are we going to get here? So let's work that out really quick. If I go 1 minus E, and the time I want is whatever time 0.693 RC is, divided by RC, I'm going to end up with RC canceling out, and I get 0.49996, approximately 0.5 times Vs equals the voltage across the capacitor. So our original formula is telling us that the amount of time, whatever you put in for RA and RB and C, that this amount of time is enough to charge the capacitor up to half of the voltage source. This is crazy, right? It doesn't make sense, because what we said in our initial videos is that in order for the 555 timer to change states from high to low, the capacitor needed to charge up to 2/3 of the voltage source. So what's going on here? Well, remember that on the discharge side, that it's going to discharge to 1/3 the voltage source, and then it's going to charge back up to 2/3 of the voltage source. Well, still things don't seem to add up here, so let's take a different look at what actually is happening. So first, let's address the first initial charge. As soon as you turn the 555 timer on, that capacitor is going to charge up from 0 to 2/3 of the voltage source. We're not going to count that, right? Okay, because it's just the initial charge up, and after that it's going to go from 2/3 to 1/3, 2/3 to 1/3, 2/3 to 1/3. So the initial charge, it just happens once, it never happens again, it never happens that long, because the initial charge is going to take however long it takes to reach 2/3 the voltage source. Okay, so probably somewhere between 1 and 2 RC. So to make things easier, let's define our voltage source. Let's say that our voltage source is going to be equal to 9 volts. All right, so if our voltage source is equal to 9 volts, that means, according to the data sheet, that when this capacitor charges up to 2/3 of the voltage source before it changes states, it should charge up to 6 volts. And then it's going to discharge down to 1/3 of the voltage source, which will be 3 volts. So we should see a swing between 6 volts to 3 volts, back and forth across the capacitor. So let's do a little brainstorming here. Let's think about that phenomenon. If I'm charging from 3 volts up to 9 volts, then I'm really not doing what the chart is saying here, right? This has me going from 0 volts up to the full voltage source, but I'm starting at a different position. I'm starting at 3 volts here. So one way to make this reflect correctly in the formula is to say that the source that's actually charging this up is a 6 volt source, not a 9 volt source. So our voltage swing is going from 3 volts to 9 volts. That's only a 6 volt swing. It's not a 9 volt swing. Our curve is going to look a bit different. It's going to be more squashed. This whole shape that you see here is going to be squished a little bit more. So the output values are going to be a little bit different. So let's take a look at that actually in the formula. So this time VC equals 6 volts, and we're going to use the fractional time value from the data sheet, 0.0693. Again, these two RC's canceled out. This is the exponent of E. We've worked this out before. It's 1/2. So VC equals 6 volts times 1/2. So VC equals 3 volts. So what does that mean? So what this means is that in 0.693 RC seconds, the capacitor is going to charge 3 volts. So it starts at 3 volts. It's trying to charge up to 9 volts. So in that amount of time, it's only going to charge 3 volts. So we ended up with VC equals 3 volts, but remember, we already had 3 volts in the capacitor because we didn't start at 0, we started at 3 volts. So that says that in that 0.693 RC seconds, that there's going to be 6 volts across the capacitor. That is 2/3 of the 9 volt source. And so now it's going to start to discharge. So I hope you can see what's going on here. The formula that we started with, we said that this is kind of problematic because this is only going to allow that capacitor to charge up to half of the voltage source given this amount of time, 0.693 RC. But if we look at it from a different light and notice that the 555 timer will never let the capacitor voltage get to 0 volts, instead, it's only going to let it get to 3 volts before it needs to charge up again, that then this formula is correct because we only have 6 volts that we need to charge up from 3 volts to reach the source voltage. But if the 555 timer only lets it charge up to 0.693 RC, then it's only going to let it charge up from 3 volts to 6 volts, and then it's going to turn back around, discharge to 3 volts, charge up to 6 volts, discharge to 3 volts. And that's what we're trying to show here. That's where that 0.693 comes in. Likewise, when the capacitor discharges, it has a similar sort of curve. We're not going to get into it so much, but it does pretty much things in reverse. Drawing this off the cuff, so it's going to be crappy. Remember, it's not discharging from VS, which would be 9 volts. It would be discharging from 6 volts down to 3 volts. There's another equation for this. It is given by this formula. The voltage across the capacitor equals the voltage source times E minus T over RC. And there's similar sort of math involved. You can use the same sort of logic to figure out the discharge like we figured out the charging phenomenon. Alright, if you understood very little of this, that's okay, and let's say you just want to figure out how to manipulate the formulas, or let's say you did understand all this, let's take still a look at how to manipulate these formulas. To get the total amount of time it takes for the 555 timer to go low to high, and then back to low again, all you do is add up T1 and T2. So we can do that. We'll use the value T for that. Okay, so now we can combine some terms to simplify a few things. And we end up with 0.693 times C times RA plus 2RB. Like we said, T is the total amount of time it takes for the output to be low and then high and then return to low. If we want to figure out what the frequency is, so in other words, how many times this happens per second, we can say 1 over T. That equals the frequency. And then we pretty much take this whole formula and put it over 1. Then simplify this a little further, and you end up with the formula that's in the data sheet. That's how you derive at the frequency for a 555 timer. Because so many people have commented about this, there's been a few people who've wanted to know, okay, I have a 555 timer, I want it to output a certain frequency, I have these components, you know, how do I make these components make the frequency that I want? So I'm going to do an example here. Okay, so let's say we're trying to hit a 40 kilohertz target. Okay, we want our 555 timer to output 40 kilohertz. This is real world stuff because I just made this ultrasonic transmitter that spits out a ultrasonic signal at 40 kilohertz. It has modulated audio on it. I had to make my 555 timer create a 40 kilohertz signal. So I'm aiming for 40 kilohertz. One thing that I always do is I try to always have RA equal to 1 kilo ohm for better or worse. So I had RA 1 kilo ohm. I always try to make RA much smaller than RB, because if I do that, if I make RA much smaller than RB, then that means really the only thing that has bearing on the circuit is RB. Current will go quickly through RA and then have to go through RB to charge C. When C discharges, it'll go through RB. So pretty much if you make RA very small compared to RB, then the timing difference between the discharge and the charge time is very small. So I always try to make RA much smaller than RB. Now, because of a silly fluke that happened at my last job, I ended up designing a lot of things with 820 picofarad capacitors. So when I started designing stuff at home, I kind of continued that trend. So I have a lot of 820 picofarad capacitors. And you may have a lot of a certain type of capacitor as well. This is just what I'm using in this instance because I had a bunch of these and I just got this to work. I have my frequency target. I know what I want RA to be or try to be, and I have a bunch of these capacitors. So now I just got to figure out what to do with RB. So I know I want my frequency to equal 40 kilohertz. So let's just manipulate some of these things over here and see if I can figure out what I want to do with RB. So first, I know that F equals, now I want to try to move everything over to one side of the formula to just be left with RB. So I am going to multiply both sides times C, and I'm also at the same time going to multiply both sides by 1 over 1.44. So what I'm going to end up with is F times C over 1.44, and I end up with 1 over RA plus 2RB. So now the next thing that might be helpful is to invert this so RB is on the top. So I'm going to take and inverse both sides. So 1.44 over F times C equals RA plus 2RB. Now at this point I need to move RA over to this side, so I'm going to end up with, and then finally I'm going to divide all of this by 2. So now I worked this out beforehand, but just because I always like to check myself because I've been known to make silly mistakes in the past, I'm going to take and plug my numbers in up here into this formula and see what I get. Alright, and the number that I get turns out to be RB equals 21.45 kiloohms. Okay, so now I am looking for a resistor of 21.45 kiloohms, and it happens that I do have a resistor of 22 kiloohms around, so that's what I ended up using. No, I didn't end up using it, because what I really ended up using was this large variable resistor right here. Here's the thing about a 555 timer, is you can calculate all day long to try to get the exact values that you need to hit this target at 40 kilohertz. You can breadboard it up, you can get it close, and then when you're all done with it, you take it apart and you put it on a circuit board, and you'll notice that you're always just a tiny bit off. So what I always do is I take mostly RB, I get a value like this, and then if it is absolutely critical that I be able to dial in this frequency perfect, which in this case I needed it to be because these ultrasonic transmitters like to be dialed in exactly at their optimal frequency, I will use a variable resistor for RB. In this case what I did, if I need 21 kiloohms, then what I'm going to use is a 50K potentiometer, so I can adjust it to 21 kiloohms if it's working right, and if it happens to be a little bit off, I can tweak this variable resistor just a little bit to get it within the range that it needs to be perfectly, or pretty close to perfectly, 40 kilohertz. So this is great to get you close, but remember there are factors that when you actually build a circuit come into play that may not get you exactly 100% on target of 40 kilohertz or to your target value. Remember, every one of these components has a percentage error. There could be a percentage error in the capacitor and the resistor. All those percentage errors put together could lead you off of this, and probably will. So you need to design to account for that fact. I'd like to thank you guys for all your great comments and suggestions. Thank you for watching this video, and as always, if you have any ideas for videos or any comments at all, please feel free to leave them. Thanks for watching, and I'll see you next time.